In the final part of your introduction to functional groups, we're going to go over functional group families that have a carbonyl present in them, and we'll also talk about what a carbonyl is as well. All right, our last big group is going to be compounds that have a carbonyl group. Carbonyls are usually drawn in a trigonal planar way because we have carbon double bonded to oxygen. Remember that oxygen has two lone pairs, so there's not going to be anything else that bonds to it. And then you are going to see something attached to each of these carbons to give the carbon its full octet or its 4 bonds. So let's start with the aldehyde family. The aldehyde family has to have a carbonyl group or it wouldn't be classified in this section. So aldehydes have their carbonyl at the end of a carbon chain. If you're at the end of the chain, you're not going to be attached to any more carbons. You're going to have a hydrogen at the end. That ends the chain because hydrogen can only make one bond. It has one valence electron. It's stable with 2 valence electrons in its outer shell. An example of aldehyde with actually filling in carbons with our R group would be this. And one thing that's always good to check, we haven't talked about this yet, is to just make sure that each of your carbons have 4 bonds. And sometimes that's a little bit easier if you actually draw those bonds out at first. So here I see carbon has 1, 2, 3, 4 bonds, and this carbon has 3 hydrogens on it, so it would look like this. Okay, so notice that each of those carbons has 4 bonds. Each of the hydrogen has only 1 bond, which is stable for it. Ketones get easily confused with aldehydes. They also just have a single carbonyl in them, but instead of the carbonyl being at the end of the chain, the carbonyl is going to be in between 2 carbon chains. So think of ketones as being in the middle and aldehydes as being at the end. So in this case, we would have a carbonyl wedged between 2 R groups. Notice the similarities between aldehydes and ketones. That is why they are so easily confused. So those R groups can be the same or they can be different. Does not matter. Let's just draw them for the sake of not taking 15 minutes on this podcast. Let's make them the same and we'll make them short. So we put a 1 carbon chain where each of those R groups goes. Notice that this carbon is attached to 1, 2, 3, 4 different elements, so therefore it has a full octet. And notice that that carbonyl, let's draw that a little bit better, your carbonyl is going to be in the middle of the chain, whereas the aldehyde is at the end. All right, carboxylic acids have a carbonyl, but also attached to the C in the carbonyl is going to be a hydroxyl group. So this could be any chain length attached to a carbonyl, and attached to that carbon in the carbonyl is an OH group. Now, because we're ending with an H and the H is already bonded to oxygen, we know we're at the end of the chain. So you're only going to see carboxylic acids at the end of their carbon chain. Let's go ahead and draw an example of this so you can see what it would look like. We'll do a 2 carbon chain. And it's always good to get in the habit of double checking or counting your bonds to make sure that carbon has enough bonds and you haven't overloaded it and that you've put the correct number of hydrogens on each of those. And that's something that we're going to practice a lot in the next couple of podcasts as well as in class. So again, what makes this a carboxylic acid is the presence of this group, this carboxyl group. All right, esters get easily confused with ethers. And let's see why. An ester has a carbonyl that is in between 2 carbon chains, but it also has a single oxygen. So we have our carbonyl, we have an oxygen, and then we continue a carbon chain. So notice that you have a carbonyl and an oxygen in the middle of the chain. If you think back, and I really don't want to confuse you, but ethers, if you remember, are a single oxygen in between 2 carbon chains. So what makes the ester different is the presence of the carbonyl with the single oxygen. So it has both of those features. Those two are very easily confused, Make sure that you know the difference between those. To give you an actual example of an ester in a molecule, we can do a short chain. We have our carbonyl, our oxygen, and then another carbon chain of any length. And I'm just using a single carbon chain here to make it easy, but that could be 20 carbons long, it can be 1 carbon long, just so long as it's in the middle of a carbon chain. It has a carbon chain on either side. All right, our last group are the amides, and amides, I will tell you right now, get easily confused with amines as they both contain an oxygen. So the amide group has a carbon chain of any length attached to a carbonyl, or it wouldn't be in this classification group. That carbonyl is directly attached to a nitrogen atom. This nitrogen atom, remember, it has 2 lone pairs. It can be either attached to a hydrogen or a carbon, and another hydrogen or a carbon. This can be kind of confusing and challenging at first, so it can be in the middle of a chain, or it may be at the end if it is attached to all hydrogens. I will show you a more simple example of this to put in your notes so you can start to recognize these. Oh, I'm doing R groups again, hang on. All right, so we have a carbon chain with a carbonyl in the middle, and then a nitrogen group. And just for the fun of it, let's make it attached to 2 R groups. Okay, so again, what makes this an amide? It's an amide because it has a carbonyl and a nitrogen directly attached to each other. That's your identifying group. That's what makes it part of the amide family. Remember that amines are simply an R group with a nitrogen. There is no carbonyl. So make sure you know the difference between those. So that was a lot of talking about recognizing functional groups, and we just talked about letters and elements a lot. Let's look at what this might look like on an exam or in a practice problem or on your homework. So you are going to get a structure similar to this one that is written below the word practice. So the first thing I'm going to look for is anything other than a heteroatom, so something other than carbon and hydrogen. If there isn't one, I know it's either an alkane, alkene, alkyne, or an aromatic. So here I see the presence of this OH group. So that tells me right now that's a heteroatom. So it's not, I'm not going to classify this as being an alkane, alkene, alkyne, or an aromatic. It is something else. It belongs to our second group, which are compounds that have a single heteroatom. And if you look at back in your notes, OHs tell us that this is part of the alcohol group. So I would classify this molecule as being part of the alcohol family. All right, so I have 2 more examples. I am going to go ahead and put the next one up. What I recommend is for you to pause me. See if you can't find all the different functional groups that are present, list them, and then hit play again and see if we got the same answers for the next 2 problems. All right, so right away, I am seeing a lot going on. I see this structure. And we haven't had a chance to talk a lot about this structure, but that's a benzene ring. It's all carbons and hydrogens, and because it's in that specific order, benzenes belong to the aromatic family. So I know I have an aromatic functional group here, but that's not all that I have. Looking over at the rest of the structure, I also see a double bond right here. That double bond is between 2 carbons, so there's no heteroatoms, there's no carbonyl, it's not carbon double bonded to oxygen. So that tells me that we also have an alkene present. It's very important that we put the E there because an alkene is different from an alkane, is different from an alkyne. And so it'll be really important as we move through this that you really pay attention to details. Let's try another one. All right, in our last example, I'm looking for anything other than carbon and hydrogen. And I see that on the ends. I see that we have an NH2 group here and an NH2 group here. All right, so that reminds me of 2 that we easily confuse. It's either an amine or an amide. And in this case, because you don't have a carbonyl present, this is an amine. So I would classify this molecule as being part of the amine family because the presence of the single nitrogen, if it had a carbonyl, a C double bonded to O right next to nitrogen, we would call it part of the amide family, but it does not, so it is an amine.